Welcome to Unit 5, Chemical Reactions. I'm so excited to be here with you guys. What we are going to be learning in this unit is going to be so critical and foundational to everything else we are going to be learning the rest of the school year. And obviously, everything we've learned so far has been important too, but this one especially, you really need to get this down. And if you're not getting it down, you need to come in for extra help because this will matter for the rest of the year. Okay, so we're going to be learning about chemical reactions. We're going to learn how to write them, how to balance them, how to classify them. And then we're also going to be talking about a couple of other interesting things with chemical reactions in Concept 3, but we'll get to that eventually. For now, we're just going to learn how to write reactions. How do we write out chemical reactions? So before we get there, let's remind ourselves, what are chemical reactions? So we have to go all the way back, throwback to Unit 1, Introduction to Chemistry, where we learned about the difference between physical changes and chemical changes. So a physical change is a change in a substance that doesn't change its identity. So you could take, liquid water from your cup that you have right now. You could boil it. You could take an ice cube and you could melt it. You could vaporize something, you could grind up, you could have a sugar cube and grind it up into a powder. All of those things would be physical changes. They would not change the identity of those substances that you are manipulating. Whereas a chemical change is the change of a substance into another substance. It is when a chemical reaction occurs and we make something new. We change the identity. So when you burn something, when something oxidizes, rots, ferments, these are all examples of chemically changing things. And so we said when a chemical reaction occurs, that's a chemical change. And so we need to define chemical reaction, especially since that is the title of this entire unit. And I have given you a definition for this before, but we're going to add on to it a little bit in this unit. We're going to keep building on this in our understanding. So for this unit, I want you to know that a chemical reaction is the process by which substances collide with enough energy that new bonds are formed between atoms. Thus, we are creating new substances. And two things that are really important to remember with this are chemical reactions do not have a change in the amount of matter, okay? The matter itself is not really changing, which we'll be talking about throughout this concept. There is a change in energy, which we'll be talking all about in its own unit, Unit 10, Thermochemistry. But energy does change, so we'll get there in a little bit. Now, something that's important to understand, because I mentioned back here that they have to collide with enough energy. That comes from the collision theory, which is that reacting particles must collide in order for a chemical reaction to occur. And they must do it with enough force or energy to change something. Okay, so a lot of substances can't just be like put in a beaker and then a chemical reaction happens. Okay, they have to be made to collide with enough energy to react. And so a lot of times that means, we have to do something. Maybe we have to add heat. Maybe we have to add electricity. We have to do something in order to make this reaction happen. So they can collide without actually reacting if there isn't enough energy. Now, the rate of a chemical reaction, which has to do with the chemical reaction's kinetics, depends on the frequencies of these collisions, which again, we're going to be talking about a lot more in Unit 10. But I just wanted to make sure you knew that how fast these reactions happen depends on the amount of energy that's making these collisions go down. Now, you may be thinking, well, how do I know if a chemical reactions happen? How do I know if it's a chemical change versus a physical change? And like we said, when there's a chemical change, a chemical reaction has occurred. And there are some signs that this has happened. What's happening chemically on a macro level, what we're seeing with our eyes, informs what's going down on the micro level. Now, there's got to be more to it. You do have to think about what's happening. You can't just see some of these evidences and say, oh, for sure a chemical reaction has happened. That's not always the case. But typically, if you see one or if you especially see two or more of these things happening, most likely a chemical reaction has occurred. Okay, so some of those signs are energy change in this system. You can tell that energy has changed. So one way we can see this is, a sudden release of light, a flash of light, or If heat is released or absorbed, that's going to be an energy change and it's going to result in a sudden temperature change. You're going to feel that absence of heat and that the beaker is going to feel cold, or you're going to feel that heat being released as it feels warmer. So those are signs that energy has changed, and that would be a sign that a chemical reaction has occurred. Also, a sudden color change can be evidence of a chemical reaction. An odor change, a gas release, we call this effervescing. If there's effervescence, if those bubbles are forming, that's typically a sign that a gas has been formed, which again, that can be evidence of a chemical reaction. But we also know if it's just a phase change, like if you're just boiling water, you're changing liquid water to gaseous water, that is not a chemical reaction. So that's where, again, these can be tricky. These aren't the end all be all. You still have to think about it, but these are typically signs that a chemical reaction has occurred. Another one is the sudden appearance of a solid, and that solid that forms is known as a precipitate, and we'll define that in more detail later. But basically, when you mix two aqueous solutions together, they can form these precipitates, and that is a sign that a chemical reaction has occurred. Now, we need to talk about the law of conservation of mass, which is also known as the law of conservation of matter. But what this states is that matter cannot be created or destroyed. It can only change forms within a system. So we said at the beginning that even in a chemical reaction, even in a chemical change, there's not a change in matter. We know that to be true because of this law of conservation of mass. So what that really means when you're looking at a chemical reaction, we're looking at an equation to represent that chemical reaction. The mass of the reactants or your ingredients should equal the mass of the products. They shouldn't just be disappearing, okay? They're just going to be changing forms. So for example, if you have 25 grams total of reactants that you're reacting together, you should end up with 25 grams of products made. Another way of looking at this is if there are 2 oxygen atoms in your reactants, you should see 2 oxygen atoms in the products. And this is where balancing equations become so critical. And that's kind of where we're going to transition for the rest of this concept. So before we do that, we're going to do a little inquiry lab activity in class that I think is going to really help you visualize and understand this. But for the sake of the notes, we're going to keep moving forward in our video. So let's talk about writing these equations. I mentioned that equations are used to represent chemical reactions, to represent chemical changes. They also can be used to write out physical changes as well. I want to make that clear. They can be used for both. But for our purposes in this unit, we're talking about chemical reactions. So that's what we're going to be writing equations for. You can write these equations in word form or in formula form. And really, an equation is just like a recipe. It's just telling you what's going in, how much is going in, and then what is going to be made. We're just writing chemical recipes here. So when I say it can be written in word form or formula form, here's what I mean. Here's an example of a word equation. You could say hydrogen gas and oxygen gas react to form liquid water. That is a chemical equation that you've written out that's representing a chemical reaction occurring here. But another way we could write it would be with formulas, which we learned a lot about in our chemical bonds unit, in our last unit, is how to write those formulas and what these names mean. So here's how I would write this out. Hydrogen gas, right here, you may remember from our last unit, there are certain elements that always exist in a diatomic state. So they exist in 2. They never just exist as hydrogen in the atmosphere. It's always H2. It's always O2. So we write that those are gases. They're going to react to form liquid water. And you'll notice these bigger numbers here. You might be like, what are those? That comes with the balancing, which we're going to be talking through for the rest of it. So don't get caught up like this is a foreign language. I'm going to teach you how to write these. For now, I just wanted you to see the difference between words and formulas and what those look like. Okay, so now let's learn the notation that's used to represent these reactions happening when we're writing in formula form so that you can do something like this yourself. I could give you these purple words and you could write these teal words or vice versa. Okay, so here's an example. We're going to use this equation of solid sodium and gaseous chlorine reacting to make solid sodium chloride to kind of break this down and identify what each of these pieces are. Okay, so first, your reactants are your starting substances. Those are your ingredients. So think about this like if you were going to make chocolate chip cookies from scratch, your reactants, your ingredients would be butter, sugar, chocolate chips, probably some flour, maybe an egg. Those are the kinds of things that you'd be mixing together in your ingredients. We typically see them to the left of our arrow here. The products are our ending substances. They are what is made by the reaction. So For chocolate chip cookies, it would be the actual cookie dough or the chocolate chip cookies you make at the end of it. That would be your products. The plus sign is what separates one or more reactants in products. So you can see it right here, it's highlighted. So that's going to separate your sodium from your chlorine so you can keep track of them. This plus this. And then your arrow, that is going to represent yields or produces or makes. It's going to show these things are going to mix together and make this thing, or they're going to react together and make this. So that's what that arrow represents. You're going to read that in your head as yields. Now, the coefficient, that's what those big numbers are. They tell us the number of each substance needed. So I have them highlighted here. We need 2 sodiums, and they're going to make 2 sodium chlorides. Now, you might be thinking there's nothing in front of this chlorine. Remember, in chemistry, when we don't see something, typically that just means that there's a 1 there. We're just not going to write that out, okay? So if there's not a number, it's understood that it's 1. Just like in sodium chloride, where right here I don't see a 1 and a 1, we know that there are 1s there. Now, coefficients, these orange numbers can change. We are going to change them in order to balance reactions, but subscripts cannot change. So subscripts, remember, are our little numbers here that are going to tell us how many atoms are in a compound. So like sodium chloride is 1 atom of sodium to 1 atom of chlorine. That's the ratio of those. That cannot change. If it changes, it's no longer sodium chloride. Okay? And again, if only 1 is needed, the 1 is not written. That's what we see here in our chlorine gas. Again, how to read these? The ratio of sodium to chlorine is 2 to 1 in this reaction. So if we're looking here, we have 2 sodiums for every 1 chlorine. That's what we need for this reaction to occur. Just like if you're thinking about the cookie dough, you need 1 cup of chocolate chips for every, 1 stick of butter and for every 2 cups of sugar. Okay, so it'd be a 2 to 1 to 1 ratio. If you have 2 sticks of butter and you want to use all of that to make cookies, you're going to need 2 cups of chocolate chips and 4 cups of sugar. Okay, so it's just telling you the ratio of these ingredients together, so you can scale it however much or little you want to make, but it's got to be in this proportion. Okay, the other notation we see here in parentheses, that represents the state of matter for each substance. So for example, when I'm making cookie dough, do I put in a solid stick of butter or do I need a melted liquid stick of butter when I'm mixing it up? It depends on the recipe. And so this is basically telling us in our recipe what form they need to be in order to react. So an S in parentheses represents solid. We see that here in our equation. An L represents liquid. We don't have any liquid in this equation. A G represents gas, which we do have here. And then AQ represents aqueous, which means it's dissolved in water, and it needs to be in order for these things to react. Now let's put this all together. I have color-coded the equation based on all the colors I was using on the previous slides. To help my visual learners out there, if that's overwhelming to you, don't worry about the colors. They are intentional, but it's okay if you don't like them. And I'm basically just going to read this out loud. We'll walk it through. We'll write the words here of what this means, because you're going to get better at this, at taking the chemical language, the chemical equation language, the formula language, if you will, and translating it into words. That's what we're going to do now. So this is how this is read. This says 2 solid sodium atoms, or 2 sodium atoms that are solid, if you want to make sure you're going left to right, reacts with 1, because remember the 1's understood, chlorine gas molecule, to yield or make 2 solid sodium chlorides, or 2 sodium chlorides that are solid. That's how you would read this. Okay, now again, this gets easier with practice. So that's what we're going to do next on these next few slides. We are going to go through this, and I'm going to give you a bunch of practice problems. I don't want you to just look at the answers. I want you to actually try that for yourself and see if you can figure them out, and we'll go over them in class together. And then we're going to do an activity that I think is going to help you learn how to balance these. But again, for the sake of the video, we're going to just kind of keep moving forward. So hopefully the activity we do with the candy will be fun and it'll help you understand how to balance. But for now, we're going to learn how to balance. How do we figure out what those coefficients are that we've already talked about when we're writing equations? So we have to balance equations so that the law of conservation of mass is not violated. Remember we said, if you start with 2 oxygen atoms, you need to end with 2 oxygen atoms. If you end with 2 sodiums, that means you must have started with 2 sodiums. They can't just come out of nowhere. Okay, so that's where balancing helps us. We use coefficients to do this. Why? Because coefficients can be changed. Subscripts cannot. Okay, remember, we can change these numbers at the front. We can change these coefficients. We cannot change these subscripts. Changing the subscripts changes the identity of the reactants and products. Changing the coefficients just changes the ratio of them to each other. Okay, so we'll change coefficients, big numbers. We will not touch those little numbers at all. Okay, so here are kind of some steps you can follow if you want some written out steps for how to balance equations. First, you'll write the equation for the reaction out. You'll write it out in formula form. This may already be done for you. If it tells you in words what the states of matter are, the gas, liquid, the solid, the aqueous, you can put those in. If it does not tell you, you're not expected to guess in my class, okay? You don't have to write them if I don't tell you. Again, but this first step may be done. I may just be giving it to you and I just may say balance it. Then you can go ahead and balance it, okay? Next thing you're going to do is you're going to put the symbols of each element in a column under the reactants and products and keep your polyatomic ions together if possible, okay? So if you see, a phosphate ion, PO4, keep it as PO4 if you can. Don't separate it out into P's and O's. That will make it more complicated. Only do that if you have to. Then you're going to count the number of each atom on both sides of the equation and write it in your chart. And then you're going to change the coefficients only on either side of the equation to balance the number of each atom. You're going to keep track of what your totals in your chart. And then until all of the totals are the same. And then at the very end, you'll look at your answer and see if you need to reduce the coefficients as needed, because we always want the simplest form. We don't want it to say you need 2 of everything. Well, if you needed 2 of everything, that means you could also just need 1 of everything. So you could reduce those. Okay, so we'll always check that out too. And we'll practice this together, but it always needs to be in the lowest whole number ratio. Okay, let's do an example. That will make this much easier. And again, if you're doing these notes prior to having done that activity with Candy, this is going to feel a lot more overwhelming. I promise that the Candy activity will really help this make more sense and you'll be able to visualize it better. But let's just keep going for the sake of the video. So let's do an example. All right, let's read this out loud. We've got solid iron reacts with chlorine gas to yield or make iron 3 chloride. Iron's a transition metal, so we need to be able to say what its charge would be. That's solid. So solid iron 3 chloride, okay? But we need to balance this. So first, the equation's written for us, so step 1 is done. Now we're going to make our little chart, okay? This is how I do my little chart. Reactants and products with room in the middle. In the middle, I list all of the different atoms. So look to the left side of the arrow. What is in this equation? We've got iron and we've got chlorine. Okay, look on the right side. We've got iron and we've got chlorine. There should be the same atoms on both sides. Now we're going to write how much are we starting with each of these. So look at your iron. I'm starting with 1 iron, okay, and I'm starting with 2 chlorines. I'm ending with 1 iron right now. This shows 1. Let's look at our chlorines. We start with 2. We're ending with 3. Now look at these. If these numbers already match, that means you're already balanced. The iron is balanced, but look at our chlorine. That's not balanced. We cannot start out with 2 chlorines and end with 3 chlorine atoms. That's not possible according to the law of conservation of mass. So something has to happen. We need to balance these. So we need to add some coefficients to do that. Now, think of coefficients just like in math, like you're going to be multiplying the whole thing by these. So think about a least common multiple of 2 and 3. Well, that would be a total of 6. So if I multiply chlorine gas by 3, that gives me 6 chlorines on my reactant side. Well, how do I get 6 chlorines on this side? I would have to add a 2 to the front. 2 times 3 gives me 6. Now notice though, this distributes just like you do in math. So if it gives me 6 chlorines, it also now gives me 2 irons. So my chlorines are balanced, but my irons are not. So now you need to put something here in order to balance the irons on the reactant side. Well, what can I times by 1 to get 2? 2. So I check, look, am I balanced? Do I have the same amount on each side? Yes, I do. 2 to 3 to 2, is that the lowest multiples this could be? Yes, it is, so I don't need to reduce. Now, if this said 4, 6, 4, yes, I would need to reduce this to 2, 3, 2, but I don't in this instance, so I'm good to go, and that's my final answer. 2 solid iron atoms react with 3 chlorine gas molecules to make 2 solid iron 3 chlorides. Again, 2, 3, and 2 are the lowest, so you don't have to simplify anymore. All right, let's do another example. This one is going to require us to do all 5 steps because I don't have the equation in formula form just yet. So aqueous sodium hydroxide and aqueous calcium bromide react to produce solid calcium hydroxide and aqueous sodium bromide. Okay, do not check out and do not get overwhelmed. Yes, this is a lot of words, but you can do this, okay? So let's start. Sodium hydroxide That's NaOH. You're just doing what you've already done in previous units. We'll put the AQ next to it for aqueous. And so plus aqueous calcium bromide. Okay, calcium bromide, that's CaBr2, and it's aqueous, you'll have to put that. React to produce, that's my arrow. Solid calcium hydroxide, so CaOH2 with the solid symbol, and aqueous sodium bromide, NaBr. Okay, so we're going to write it out this way. Remember, if you're like, well, I don't remember how to get from calcium bromide to CaBr2. Remember, you should see that this is an ionic compound with a metal in it. You would write Ca with a 2 plus charge, Br with a -1, crisscross applesauce. That's where we get CaBr2. Remember, with our polyatomic ions, we always put them in parentheses so that the whole thing gets that calcium's 2 plus charge. Okay? So that's how we would do step 1. Step 2, now we're going to write this out. So I'll write out every element that I see in my equation. Okay, so I've got sodium. Now, you could separate this oxygen and hydrogen, but remember what I said. It's easier to keep the polyatomic ions together. So write it as OH, because notice it's OH on the reactant side and it's OH on the product side. So keep it together as the polyatomic ion, hydroxide. Then we got calcium, we got bromine. Okay, now let's keep track of how much we're starting with everything. On the reactant side, we got 1 sodium. On the product side, we've got 1 sodium. On the reactant side, we've got 1 hydroxide. On the product side, we have 2. On the reactant side, we have 1 calcium. On the product, we have 1. And then on the reactants, we have 2 bromines. And on the products, we have 1. So our sodiums are balanced and our calciums are balanced, but our hydroxide and our bromines are not. Now, you can kind of decide where you want to go with this first. If I go ahead and put a 2 here, that's going to give me 2 sodiums on the reactant side, but it's also going to balance my hydroxide. So now I have 2 hydroxides. Okay, so we fixed one problem, but we added another. Now I've got to balance my sodiums and my bromines on the product side, but look, they come together. So all I have to do is put a 2 there. That gives me my 2 sodiums. That gives me my 2 bromines. I'm good to go. I don't need to simplify any further because 2 to 1 to 1 to 2 is already as simple as it could be. And now you have a balanced equation. Okay, we are going to practice this so much. You're going to be so sick of it. You'll be like, I've practiced so much. I never need to practice this again. So if you feel overwhelmed, this is truly a situation where practice makes perfect. And we're going to do exactly